Hello, welcome to 4.1, Antiderivatives and the Indefinite Integral. Now we spent the first part of this class, in fact with the first two chapters, developing the whole concept of the derivative. Then in chapter 3 we applied the derivative. Now what we're going to do is go the other direction, do the antiderivative. It's the opposite process to taking the derivative. So, definition of antiderivative: a function f is an antiderivative of f on an interval I if f prime of x equals f of x. So this is capital F prime of x equals little f of x. I know it's confusing. I don't know why the book did that, but that's pretty standard for the textbooks. For all x in the interval I. Representation of antiderivatives. If f is an antiderivative of little f on the interval, then g is an antiderivative of f on the interval I if and only if g is of the form g of x equals capital F of x plus c for all x in I where c is a constant. The reason we include a constant, c, added to the antiderivative is because the derivative of a constant is 0. So the constant could have been 0. It could have been something else. We don't know. So when you do an antiderivative, the rule is always add a c. So c is called the constant of integration. General solution: the family of functions represented by g, that is, the family of functions represented by the antiderivative plus c, will be the general solution. The differential equation is an equation that involves x, y, and the derivative of y. And there's a whole class on differential equations that follows Calculus 3. I encourage you all to take it. Even if you don't need it, it's just good to have that knowledge. The antiderivative of a function, say f of x equals x squared, is a function that, when we take the derivative, we end up with f of x. So to find the antiderivative, we must reverse the steps. So the power is 2. It must have been 3. So the antiderivative, it must have had a 3 as the power. Also, if we took the derivative of a function with the power of 3, we would then multiply the former power by the x squared. But since there's no coefficient of 3, the original polynomial must have had a coefficient of 1/3 to cancel. So therefore the antiderivative is f of x equals 1/3 to the x cubed. Why? Because the derivative of 1/3 to the x, 1/3 times x cubed, is 3. The power comes out front, times 1/3 times x squared. This is taking the derivative. That cancels. 3/3 becomes 1. You get x squared. So the rule is, when you take the antiderivative of a variable to a power, you will add 1 to the power and divide by the new power. So find the general solution of the differential equation y prime equals 5. That means that y prime equals 5 times x to the 0, because x to the 0 is 1. So that y must have been 5 times x to the 0 plus 1 divided by 0 plus 1 plus c. 5 times x to the 1 plus c, or just y equals 5x plus c. Because the derivative with respect to x of y will be the derivative with respect to x of 5x plus c. So y prime is 5 times x to the 0 plus the derivative with respect to x of c. So y prime equals 5. That's a check. Okay, notation for antiderivatives. If dy dx equals f of x, then it can be convenient to write this in the equivalent form, differential form, dy equals f of x dx. But for the antiderivative, we can write y equals, this is an elongated s. Had the computer draw that, it looks like this. It stands for infinite sum. Integral of f of x dx, which is capital F of x plus c. So f of x is called the integrand. Dx represents the variable of integration, and c is the constant of integration. Note the term indefinite integral is a synonym for antiderivative. So basic integration rules. The integral of f prime of x dx is equal to f of x plus c. integral of little f of x dx is f of x plus c. If that's the case, then d dx of the integral of f of x dx is just f of x. The derivative with respect to a constant is 0. Just remember these differentiation issues. Derivative with respect to x of kx is k. The derivative with respect to x of k f of x is k f prime of x. The derivative with respect to x of f of x plus or minus g of x is f prime of x plus or minus g prime of x. d dx of x to the n is n x to the n minus 1. d dx of sine x is cosine. d dx of cosine is negative sine. d dx of tangent is secant squared. d dx of secant is secant x tangent x. d dx of cotangent is negative cosecant squared x. And d dx of cosecant x is negative cosecant x cotangent x. So with that in mind, we have the integration formulas. The integral of nothing dx is a constant. The integral of k dx is kx plus c. The integral of k times f of x dx, you can factor the k out and you have integral f of x dx. The integral of f of x plus g of x dx is the integral of f of x plus dx plus integral of g of x dx. The integral of x to the n dx is x, you add 1 to the power x to the n plus 1 over n plus 1 plus c, as long as n is not negative 1. That's a special case we'll get to later in chapter 5. The integral of cosine x dx is sine x plus c. Integral of sine x dx is negative cosine x plus c. Integral of secant x dx, secant squared x dx is tangent x plus c. Integral of secant x tangent x dx is secant x plus c. Integral of cosecant squared x dx is negative tangent x plus c. And our integral of cosecant x cotangent x dx is negative cosecant x plus c. So example 2 says describe the antiderivative of 4x. Well, that's going to be 4 times the integral of x dx. That's going to be 4 times what? This has a power of 1. So it'll be x to the 1 plus 1 divided by 1 plus 1 plus c. It's 4x squared over 2 plus c, which is 2x squared plus c. Okay, so the pattern for integration, you have the original integral, you rewrite, you integrate, you simplify as needed. For example 3. Rewrite before integrating, we have the integral of 1 over x to the 4th dx. That's the integral of x to the negative 4 dx. That becomes x to the negative 4 plus 1 over negative 4 plus 1 plus c. So that's going to be x to the negative 3 over negative 3 plus c. And you could write that as 1 over negative 3x cubed plus c. Either one of these. Here we have the integral of the cube root of x dx. I'd write that as the integral of x to the 1/3 dx. That would be x to the 1/3 plus 1 over 1/3 plus 1 plus some constant c. That would be x to the 4/3 over 4/3 plus c, which I'd probably rewrite as 3 times the cube root of x to the 4th over 4 plus c. Integral of 3 cosine x dx, I'd say 3 times the integral of cosine x dx. That's going to be 3 sine x plus c. And that's no other way to really simplify that, 3 sine x plus c. Okay, can we go on to the next page? Okay, integrating polynomial functions. Integral dx is an integral of 1 dx, so we could write that as 1 times x to the 0 plus 1 over 0 plus 1 plus c, which is just x plus c. Integral of 2x plus 3 dx is integral of 2x dx plus 3 dx. That becomes 2x to the 1 plus 1 over 1 plus 1 plus c1 plus 3x to the 0 plus 1 over 0 plus 1 plus c2. That's going to be 2x squared over 2 plus 3x plus c1 plus c2. Now, I do this time. You don't have to do this in the future. c1 plus c2, you only need one c in the very end. So I'd write this as x squared plus 3x plus c. You don't need a bunch of c's. One c is sufficient. Integral of 4x cubed minus 6x squared plus 2x minus 1 is the integral of 4x cubed dx minus the integral of 6x squared dx plus the integral of 2x dx minus the integral of 1 dx. And you could do this all in one string if you want. So this would be 4x to the, it's 3, you add 1 to 3, you get 4 over the 4, minus 6x to the, it's 2, becomes 3 over 3, plus 2x to the, it's 1 power, becomes 2 divided by 2, minus x to the 1 over 1, plus some constant. This becomes x to the 4th minus 2x cubed plus x squared minus x plus c. Okay, next one I failed to type on here, or I think I erased it when I was messing with my notes. This is the integral of x squared plus 1 over the square root of x dx. So this becomes x squared over x to the 1/2 plus 1 over x to the 1/2 dx. And notice I put this in parentheses. It doesn't need it here because a fraction bar implies one term, but we have two terms, so put them in parentheses. This becomes integral. This is to the 2 power 1/2 power. That becomes x to the 3/2. 2 minus 1/2 is 3/2. Plus x to the negative 1/2. So we have the integral of x to the 3/2 dx plus x to the negative 1/2, dx. This gives us x to the 5/2 divided by 5/2 plus x to the negative 1/2, well, negative 1/2 plus 1 is 1/2 over 1/2 plus c. So we end up with 2/5 x to the 5/2 plus 2x to the 1/2 plus c. So note, when integrating quotients, do not integrate the numerator and denominator separately. This is no more valid in integration than it is in differentiation. So we have to follow a little different process. We have to integrate the whole thing at one time. And there are some rules we're going to learn over time. I think it's in the end of this chapter we'll get to something called substitution. I'm going to go ahead and scroll up. Feel free to pause. So here's example 6. It says rewrite before integrating, and I again must have deleted it. So here it comes. It is the integral of cosecant x over sine squared x dx. So I would mess around with this a little bit. I'd call this the integral of cosecant x over sine x times 1 over sine x dx. And then we'd have the integral of cosine x over sine x is cotangent x. 1 over sine x is cosecant x dx. And this fits in with one of those antiderivative formulas. This becomes negative cosecant x plus c. Now, we've been solving general situations, and that's why we have a plus c. If we have an initial condition, we're told like, well, f of 3 is something else, or f of 0 is something. We can get what we call the particular solution, the solution for one specific situation. So a particular solution, a specific, not general solution to integration. This form will not contain the general term c, but contains some constant, which may be a 0. And the initial condition is information given about a problem in order to get a particular solution. So let's go on to our last page of this section. So in this case it says solve the differential equation. So differential equation sounds really intimidating, but it's not. H prime of t is 8t cubed plus 5 with the initial condition h of 1 is negative 4. So the integral of 8t cubed, so h of t would be this integral of 8t cubed plus 5 dt. Look, I'm putting the parentheses there. That becomes 8t to the 4 over 4 plus 5t plus some constant c. And that's going to be 2t to the 4th plus 5t plus c. So h of 1, well, h of t is going to be 2t to the 4th plus 5t plus c. H of 1 is 2 times 1 to the 4th plus 5 times 1 plus c, and that's negative 4, it says. That means we can solve for c. 2 plus 5 plus c is negative 4. 7 plus c is negative 4. c is negative 11. So h of t is 2t to the 4th plus 5t minus 11. This is the particular solution given this initial condition. And now we're going to go on to the last problem. So pause if you want to pause. Okay, this one is, I like this one. It's about trees. I'm a big tree fan. Tree growth. An evergreen nursery usually sells a certain shrub after 6 years of growth, and shaping the growth rate during those 6 years is approximated by dh dt is 1.5t plus 5, so that would be h prime, where t is the time in years and h is the height in centimeters. The seedlings are 12 centimeters tall when planted, so t equals, time being 0, they're 12 centimeters. So find the height after t years. So h of t is going to be the integral of 1.5t plus 5 dt. That's 1.5t squared over 2 plus 5t plus some constant c. So our h of t is going to be 0.75t squared, that's that reduced, plus 5t plus c. Now we know here at h of 0 we are at 12 centimeters. So h of 0 is 0.75 times 0 squared plus 5 times 0 plus c is 12. That tells us that c is 12. So our height function is going to be 0.75 t squared plus 5t plus 12. Now how tall are the shrubs when they are sold? They're sold after 6 years. So the height after 6 years is going to be 0.75 times 6 squared plus 5 times 6 plus 12. And that's going to be 69 centimeters. Okay, that'll do it for antiderivatives and indefinite integration. Hope you enjoyed that. I hope you're learning something here. We're moving right along here. We're over 60% of the way through the semester, so I'm having fun. I hope you are too. Thanks.